Alright, thanks for coming. Today, I'm talking about Intro to Tropical Geometry. It's part 1. I'm also talking tomorrow at Mark's for part 2. So if you find this interesting, come tomorrow at 1, nope, 11, 1. 1, thank you. In 201, Weber 201. Cool. I'll say that again at the end, just to hype it up. Because people need to come, because it's a fun seminar to come to. Okay, so first off, what is tropical geometry? There's different slogans for it. One of the slogans is it's the combinatorialization of ordinary algebraic geometry, which basically is saying people take hard things in algebraic geometry and they move it over, they tropicalize it, and then it's easier to study. Where did the name come from? I've heard two reasons as to where the name came from. One is the French named it after the Brazilians that are doing tropical geometry because they were like, these people are doing fake math, it's tropical math. What I also heard is that this mathematician, or computer scientist actually, named Imre Simone, I'm gonna guess, Brazilian computer scientist. He lived in Sao Paulo, which we don't know is in Brazil. And what goes through that city is the Tropic of Capricorn, which below the Tropic of Capricorn is the tropics, above it is not. He worked on one side, lived on the other side, so he traveled across the Tropic of Capricorn every day. So whether the math is tropical depends on whatever side he was doing his work on. But yeah, that's a fun little fact. Okay. So today we're going to start by looking at the tropical semiring. Which is denoted with a bold T. And this is the real numbers with negative infinity. And we have some sort of addition, some sort of multiplication on this. So our tropical addition is A plus B is defined as the maximum of A and B. This is a choice you make. Some people use minimum, some people use maximum. It's a choice you make. Today we're using maximum. A times B is defined as A plus B. We also have, if we're raising to a power, say we're raising x to the power of I, that's the same thing as doing x times itself, I times, which is the same thing as I times x, because you're adding x, I times. One thing to note about this that makes it unique is our additive identity is negative infinity, and our multiplicative identity is 0. Yes?
So if you were to do them in, would you then be unioning with positive infinity?
Yes.
Ooh.
If you come tomorrow, we're going to use min. Just to mix things up a little bit. Okay, so we're now going to look at tropical polynomials. Which is any finite sum of monomials For example, we can have 0 plus 1 times x plus x raised to the second power. You have to write 0 plus because 0 is not the additive identity. So it doesn't just go away. So this is the same thing as the maximum of 0. The 1 times x becomes 1 plus x and 2x. Another example, we can do 0 plus x plus y. This is the max of 0, x, and y. So now we want to look at what does this actually look like. And for that, we have to define the tropical plane curve. Which is denoted V of P. And that's defined as set of x's, or x's and y's, in R2 such that the max is attained by at least 2 monomials. Oh, I forgot to say, this has a name. This is the tropical line, the max of 0, x, and y. So now we're going to draw the plane curve for the tropical line. I really wish I could scroll. Oh, just kidding. Okay, so I'm going to just rewrite it. We're looking at the max of 0, x, and y. In order to find out, we have to look at different cases. So we have to look at, okay, if the max is obtained by 2 things, the max could be obtained when 0 equals x. And that would mean that 0 has to be greater than y and x has to be greater than y. So if we're graphing this, we have a line x equals 0 when y is less than 0. So that is this way. I'll underline it. The next thing we have to look at is when 0 equals y is the max. So that would be when 0 is greater than x and y is greater than x. Similarly, we have the line y equals 0 when x is less than 0. So that's this line. And then our last case is when the max is attained when x equals y. And so that happens when x and y are both greater than 0. So we have this line. So our tropical line is these 3 colored lines together. And you can have coefficients of this. So our general tropical line is anything that looks like A times x plus B times y plus C. Okay, so you can imagine, yes?
So in the definition of the tropical plane curve, you mentioned that the points are in just r squared instead of like t squared. Are you not allowed to consider like a tie for like negative infinity? Like if negative infinity is somehow maximized with polynomial in the 2 terms, does that count, or you're only allowed to plug in finite numbers?
I don't know when that would ever happen.
Like maybe if you had like x and y and x, y, and z, then if they were all negative infinity, vacuously the max would be negative infinity?
But if you had x, y, and z, the max wouldn't be attained when they were all negative infinity, you know?
What if you had x, y, and negative infinity, like instead of 0? Or is 0 always included?
0 is not always included, only if you're doing 0 plus something.
Okay, so if you had negative infinity plus something, like plus x plus y.
Negative infinity is the additive identity, so you wouldn't include it in the max.
Gotcha.
Oh, it would just go in polynomial. Okay.
It'd be
So
like
you can ignore
it'd
it.
be like adding 0 in normal. You're not going to write the plus 0 every time. That makes sense? There might be cases where it's attained, but I've never seen it.
Thank you.
Okay, so as you can imagine, we had to do 3 cases when we just had 0, x, and y. So as soon as you have some sort of tropical polynomial that has more than the max of just 3 things, this is going to be very tedious. But there's another way to do it. Which is exciting. Woohoo! Okay, so to do that, we're going to look at the Newton polygon. And so to start, we need to look at the integer lattice, which is a lattice, so we have points. This direction is your number of x's. So like here is 0, here would be x, 2x. This direction is your number of y's. So y, 2y. Here would be x times y. That's your integer lattice. So given our polynomial, we're going to look at the same one, 0 plus x plus y. We take the vertices on our integer lattice. So for this case, we have the 0, the point for x, the point for y, and we're going to take the convex hull of that. So this is our Newton polygon. And in this case, it works that our graph has a vertex in the center of this, and all of the edges are perpendicular to the sides of the Newton polygon. So we get our same line, but that only works for this triangle. You have to do one more step otherwise, and that's we're going to look at Newton's subdivisions. Okay, so for this part, we're going to look at 0 plus x times 1 plus y times 1 plus x times y. And so we can draw our Newton polygon. We have our 0 vertex, our x vertex, our y vertex, and our x plus y vertex. So our Newton polygon is this square. And now I need 4 volunteers for a demonstration. To find the subdivisions, we look at the coefficients. We need to grab a corner and a corner. But we need to make it, so this is a rectangle and we need a square. So you can figure it out amongst yourselves. How to make a square.
Wait, hold on. Fold this like here and then.
Right.
Okay, perfect. And it has to stay tight. Okay, so to find the subdivisions, you assign every person a vertex. So Kyle can be, let's see, Kyle will be 0. Wait, let's orient it for you guys. Brittany can be 0. You're x plus 1, y plus 1, x plus y. Yes, are you raising your hand?
No, I'm saying 0.
Okay, so now For the Newton subdivision, everyone goes to the height of coefficient. So since Brittany has no coefficient, she goes down to the ground. Your coefficient is 1, your coefficient is 1, so you'll stay there, and your coefficient is 0, so you go down. Where the sheet folds, which is between Ignacio and Danny, we draw a line. So our Newton subdivision looks like that. And I'll do another one. While you're up here, we can also look at, you can go back to like neutral. We'll look at 0, or not 0, sorry. We'll look at x plus y plus x times y plus -1. So we have the same Newton polygon as before because we get the same 4 vertices of 0, x, y, x times y, but now our coefficients are all 0 except Brittany. Instead of 0, her coefficient is -1, so she's going to go down and everyone else is going to stay neutral. Where does it fold? It's supposed to fold in between Ignacio and Danny again. Hard to see. But there's another fold here because our coefficients are -1, 0, 0, 0.
Let's pull that tighter.
Oh, this one's -1. There we go. There you go. Now you can see it. Sweet, thank you. So whenever you're looking for subdivisions, you have your coefficients, your vertices go up that high, you drop a sheet on top of it, wherever it folds, wherever our tent folds, you draw a line. Okay, you can just drop it.
Should we?
Okay, now that we have our subdivisions, thanks to our volunteers, we can draw our plane curves. Inside every section of our subdivision, we have a vertex. And across every line, our plane curve has to be perpendicular to every line. It has to be dual to the subdivision. So for this example, our plane curve would look like this, the red. For the other example, our plane curve is going to look the same. But that doesn't mean that they're the same graph or same plane curve, they just have the same shape. The cool thing about this is with the Newton polygons and the subdivisions, you don't just get the shape, you can get the exact graph as well. And so we'll look at that with this second example. If we pretend like we don't already know what our graph is, we'll draw our subdivision again next to it. And I'm going to label the vertices just so you remember. 0, x, y, x plus y. In order to figure out the exact location in the coordinates of the plane curve, you can look at the different sections of the subdivision. So if we first look at this triangle, you see that green, the bottom triangle? That is connecting 3 vertices. It's connecting -1, x, and y. So that part of the graph occurs when -1 equals x, which equals y, which happens at the point -1, -1. And then we can look at the other triangle. That happens when x equals y equals x plus y, which happens at the point 0, 0. So for our graph so far, we know where our 2 vertices are. We're going to have a point at 0, 0 and a point at -1, 1. From here, you can figure out the rest of the graph, but we're going to see from the subdivision first. You can do the same type of thing with all the lines through the graph. So if we just look at this edge of the graph, that happens when x equals y. And so that tells us that we're going to get x equals y line. Similarly, for the other edges,
Hang on, sorry. How did you know to connect just from x equals y to connect to the green to the blue, and not that you have an arc going away from blue or going away from green? You have to
we could
compare it.
do the same thing that we did before with the comparing, because we know the max is when x equals y. So we know that x and y are both greater than -1, and x and y are both less than x plus y. So it has to be that section. I just didn't want to write all that out again.
Sure, that's okay.
Same thing with the other edges. So the x equals -1 is going to give us this line. We're going to get a line. I should use a different color. We're going to get a line here, 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 and here. But in reality, once you have the shape from the Newton polygon and both of the vertices, you have your plane curve.
What was the difference between two examples before? Because we got the same.
We have different coefficients, or we have different coefficients, so the vertices would be in a different place.
The
If we
different
ground it.
polynomial defines the same curve.
They're gonna have the same shape, but their location in like the xy axis is not gonna be the same, because the vertices would be different. Okay. So now we're going to talk about what does it mean for a curve to be balanced. Well, the basic idea is that the edges around a vertex with something we call their weights, which I'll define, sum to 0 if a curve is balanced. So if you had something that has edges going this way and this way, if you think of them as vectors and you add them together, they're going to equal 0. This would be balanced. But we'll go through the formal thing as well. So more formally, we need that the sum of the weights, which we're calling W and EI, this is the weight of the edge, which is equal to the lattice length which from our, that's not spell length, which from our Newton subdivision, we get the lattice length from that. So it's from our subdivision, this bottom edge here has length 1. You count the number of vertices, subtract 1. That's how you find length. The edge going through it, so that means that this edge going through it would have weight 1. This edge would have weight 1 because it's going through something with lattice length 1. Cool. That's the weight of our edges. You count the lattice length, and that gives you the weight of the edge that's dual to that. And then, so we're multiplying the weights by what we call a primitive vector. And in order for our curve to be balanced, this sum has to equal 0, or the 0th there, for every single vertex. You have to do this for every vertex in your graph. Cool. A cool theorem that we have, oh, I'll do an example, actually. Example. I need a new page, actually. Example. Say we have something, I'm just going to give you the new polygon. Okay, our new polygon is this triangle. So our curve from this is in blue. We'll start with looking for the weights for every edge. The lattice length of the bottom edge is 3. So this edge has weight 3. Going up, the lattice length is 3. So that edge also has weight 3. And diagonally, our lattice length is also 3. So that edge also has weight 3. Because we're counting 1, 2, 3. Okay, and now for our primitive vectors, we're going in the direction of these lines this way. So we'll start with the one on the left. What that direction is that vector is going in the x direction, backwards 1 and up 0. So that is our first vector. I guess I'll write that right here. And that has GCD1, so we're good. The one going down is going in the x direction 0 and down 1. And then this one going up diagonal, we might be able to see right away, but we can figure it out by figuring out what's perpendicular to that diagonal edge. And that edge is going down 1 over 1. So that edge is going 1, negative 1. So we need something perpendicular to that. And to find perpendicular, you switch the coordinates and make one of them negative. So that vector is going in the direction of 1, 1. And that has GCD 1, 2, so we're good. So now to check to see if this is balanced, we're going to multiply all the vectors by the weights and add them together. So we have 3 times negative 1, 0, plus 3 times 0, negative 1, plus 3 times 1, 1. If you add that together, you get 0, 0. So we're good. This curve is balanced. Does that make sense?
And then also, sorry, in the example before, how did you compute the weight of the edge of the weight 1 on that kind of goes between like adjacent diagonal? Is that also weight 1, or is it weight 2?
Also weight 1. It just counts the number of lattice points that it goes through. It subtracts 1. Doesn't matter if those lattice points are like further away.
Okay, so like I could even go diagonally.
So like if I went from this to here,
Yeah,
that's weight 1.
that's still cool. Okay.
Good question. Okay, now we have a theorem that tells us that plane tropical curves are balanced. All of them. Which is pretty cool. So, we're going to start this proof. We're not going to do the whole thing. But this proof is by induction. So we'll start with the smallest case, which is if the Newton polygon is that small triangle. So anything that has a Newton polygon that is a triangle that looks like this is going to be a tropical line. And we can figure out if all lines are balanced. So our first tropical line was the one that just goes through like this. This triangle has area 1/2. So that's our smallest case. And this is going to be balanced from basically what we did up here. But instead of weight 3 for all of them, we just have weight 1 for all of them. So this curve is going to be balanced. But that's just one line and one triangle of area 1/2. We have to make sure that this works for all triangles of area 1/2. So we're going to start just by looking at some weird triangle of area 1/2 to convince ourselves that this is true. Say we have the same first two lattice points at 0, 0, and 1, 0. But our third lattice point is over here at 7, 1. So kind of what Jacob was saying. This still is a triangle of area 1/2. That's a great looking triangle. So all of our weights are going to be 1 here because all of our edges are length 1. They're not going to go through any other lattice points. Mainly because the only two that would be the ones going up to 7, 1. But they're only going up 1 row, so they're not going to pass through any other lattice points. So one direction vector is easy, the one that's going down through the 0, 0 and 1, 0 line, and that vector is 0, negative 1. The other vectors have to be perpendicular. So to start, we'll find one perpendicular to the top line. This one. That direction of that line is in the direction 7, 1. So we need to switch the coordinates and make one of them negative. So that direction is negative 1, 7. Then we'll look at this line. This edge is going in the direction 6, 1. So something perpendicular to that is 1, negative 6. And so if we sum these up, we get 0, 0. Something perpendicular to this new polygon would be balanced, which is good. So in order to do this for a general area 1/2 triangle, we have to make a triangle that is area 1/2. Oh no. General triangle. That's area 1/2. Okay, well we can always have our first lattice point be at 0, 0. And now let's call our other general vertices C, D, and A, B. How do we know that this triangle is area 1/2? We can look at the area of the triangle. If you take the determinant of if you look at the determinant of these two vectors that go along the outside edges, you're going to get the area of a parallelogram that looks like this. So we're going to start with taking the determinant of those two vectors. I don't know why this is writing wonky. A, B, C, C, D. And we need to cut that area in half because we just want the triangle. And so we want the determinant AD minus BC to equal 1 in order to give us a triangle of area 1/2. So multiply that by the 1/2 to get the area of the triangle. And that's the constraints that we're putting on our A, B, C, and D to get this general triangle. Now we have to find the primitive vectors to check to make sure that this is balanced. Again, one of the, or two of them are a little easier than the other two. Okay, the ones going this way and this way are going to be a little bit easier because one of our vertices is 0, 0. So the vector perpendicular to this edge is going to, make sure we're going over D and down -C. Still weight 1. This one, we're going backwards. So our first term is going to be negative. And so we're going to have negative B and A for that vector. This one is going to be the one that's a little more challenging because we need to find the slope or the direction between those 2 points, which is, let's see, A minus C, B minus D. And so we need to switch the order of those and make one of them negative. We're going to have B minus D and negative A minus C. You add those all up, you get the 0 vector, which is good. We know that every single triangle of area 1/2 has a corresponding plane curve that's balanced. From there, any Newton polygon can be broken into triangles of area 1/2. That's how you can see in the induction. We're done. Every tropical curve is balanced. It's gonna make a check, but yes.
So here you're saying that the weights are all 1.
Yes.
Is that something that you have to prove, or like is that just like
Oh,
philosophy
we know that
statement, or-
because of how we set up our triangle. In order for this determinant to equal 1, our weights have to be 1. Or yeah, that means that the GCD of the primitive vectors, that means that the GCD of all of these are 1, which means all of our weights are 1.
So you said, yeah, you skip.
I skipped that, but you can check with the determinant having to equal 1 that all of the weights have to be 1 too. And that also checks that all of these have GCD 1, because remember we need that for primitive vectors. Yes.
Is there a reason why you're picking minus C and minus B instead of minus D and minus A?
Because of the picture. So like for the minus C one, we want the y to be going down because that vector is going down. Yes, that's why.
So to do all of this, have to be like outward normals? Like could you do it with all inward normals?
I'm guessing you could do it with all inward.
But you can't like mix, like go to one of these? and
No,
the
then
other?
they wouldn't add to 0.
So you're imposing that they're all the same?
I always do them all out. It's easier to think of, at least for me, in my brain.
So you're saying a balancing condition is related to area?
In order to prove that all are balanced, you have to do it by induction of area. So we just proved the smallest case, and then from there, every Newton polygon can be broken into triangles of area 1/2. So every Newton polygon leads to a corresponding plane curve that's balanced.
So this balancing condition is something from area of triangle.
Yeah, it actually being balanced the area doesn't really matter, but in order to prove that it's balanced, you need to use area. That's all I got for you.
So you have more questions?
Yes.
What's so exciting about it being balanced? What does that do?
You know, that's a good question. I don't know. I know that it's nice, and people always say this is good because this curve is balanced, but I don't know why that's good.
Actually, that's why I asked the area is related to that.
You know? Either of you? Anyone know?
Because you use the area for
Yeah.
the smallest case of a triangle,
Uh-huh.
and then derive the balancing function from there.
Mm-hmm.
So I was kind of curious.
Yeah, I'm not sure. I'll ask. Yes.
So back to the sheet example,
Yep.
when we volunteered, so if I brought my tent and pitched my tent, could
Yep.
you tell me the tropical polynomial that corresponds to my tent?
Only if we can add weights to make it balanced. But yeah.
And
Bring in a weight rack.
Come to my backyard and we're gonna do some experiments.
Yes.
When you were doing that case where you had the lattice that was, I think it was a 4x4, and you
Mhm.
drew the drawing on that, were all of those vertices monomials in your polynomial, or were
No.
it just the edges?
Just the ones. This one?
Yes.
I mean, you could write a polynomial that had every single vertex that it was going through on it, but what you need is the outside ones. So you would need something that's 0 plus 3x plus 3y.
but like adding 2x. 2x is done.
But you could add 2x. You couldn't add, like, this one, for example.
Because then your max would be different.
Because then your convex hull would be different.
Oh, okay. Sorry.
So what's for tomorrow?
Tomorrow we're talking about tropicalization, so how to take something that's a little more complicated and move it into tropical, and tropical Bayesian theorem, which is exciting.
So you're saying tropicalization of a variety?
Yes. Any other questions? No? Okay. Tomorrow's at 1 in Weber Tool 1 if anyone wants to come.
It's also.
It'll also be on YouTube. So will this talk be. And so are other algebraic geometry talks if you're interested.
What's the name of the channel?
CSU Algebraic Geometry.
Oh, okay. Good to know.
I've heard there's a really cool Hessenberg variety talk on there.
There's a.
You can learn about Grosvenor fans, you can learn about integrals, you know.
No,
That's what I
anything you
heard
want to learn about that someone has talked about this semester.
in the last month.